Okay, so then I would say let's get started with the first talk from Prasun Mahanti from Arizona State University. He's going to tell us about doubly shadowed crater shapes within Amundsen crater permanently shadowed region.
Okay, thanks, Carolyn. Can you see my screen? Can you see the slides?
Yes, indeed.
Okay, so my name is Prasun Mahanti, and I'll be talking about crater shapes within the Amundsen crater permanently shadowed regions. I think we have heard a couple of talks on PSRs already today, but I'll just kind of talk very briefly about the permanently shadowed regions. Well, they result due to the low obliquity of the moon, and they exist in high latitude topographic lows. So, like the floors of craters at the poles of the moon. While the PSRs, they exist at the lower reaches, the upper reaches, that is the walls of the crater, they actually, the top part of the walls, they get periods of direct illumination. Some part of the illumination bounces back and forth into the PSR, but actually no direct sunlight ever reaches the PSR, due to which the PSRs have really low temperatures and have unique thermal conditions. Some of them have extremely low temperatures, such that volatile molecules which are deposited from various sources over time, for example, comets or asteroid impacts, can remain there cold trapped over a long period over geologic time. Now, the other part of this talk is actually, it's concerned with craters, and I'll just kind of go through some of the very basic points. We're talking about lunar craters, and the shapes of lunar craters, principally, they will be like kind of two parts. One of them would be simple or complex, depending on the size of the crater. There is a bifurcation around 15 kilometers, between 15 to 17 kilometers. And out of those simple craters, in this particular work, we are mostly concerned about the smaller part of those simple craters, that is somewhere around 300 meters to about a kilometer. And you'll get to know why that range kind of gets decided for us. So the shapes of the crater are initially determined by the impact itself, by the impact parameters. Say, for example, the size of the impactor, the initial velocity of the impactor, the angle of the impact, the target property there. But once the crater is formed, what happens is then the degradation mechanisms, they take over. And they again keep on changing the shape of the crater. And then it's the factors which control the degradation that changes the shape. Now, the degradation of simple craters, it can be slow and it can be fast. The slow ones, it kind of we typically try to align them with like slow diffusive processes, but you can have periods where those processes are hastened by, like, let's say, seismic activity or a nearby impact, or like a slow creep, which then fastens up because there is an impact nearby, which causes a vibration, right? But then all these processes lead to the degradation of the crater, which ultimately changes this initial shape of that crater, right? Now, in one of our earlier works, what we kind of try to summarize is that before the crater formation, the shape kind of gets decided based on the initial strength of that impact plane. Like, it could have been modified from other impacts previously. It could have a lot of different layers in that. And it might be a place where it is already being affected by seismic shaking, right? But once the crater forms, then that degradation rate, which is mostly determined by micrometeoritic bombardment, that can be increased. You can have seismic shaking actually regulating the rate after the crater formation, right? And smaller craters, because they are small, most of them basically they form only in the regolith. So the walls are really not strong, and they are more affected by all these effects. Now, at the PSRs, and at this point, I'm strictly kind of confining myself to this about not other volatiles, but just water and water ice and surface frost. There can be an effect to these target properties due to this really low temperatures, right? We could have permafrost like landforms, which are really hard, we can actually have water ice. And as some papers have indicated, we can have, like, let's say, solid thick ice, if at all. And we can actually have like a thin layer of surface frost merged with the regolith, and then you can have multiple layers as you know, as you have more and more impacts, the frost gets lower and lower in the depths of the stratum. Now, due to this, what can happen? Well, it ultimately leads to a moderation of the strength of the target, and you can have a layered stratigraphy, and you'll have large changes in the porosity. And remember that because these are PSRs, and you know, the defining lines of the PSR are drawn by the summer maximums, but over the entire cyanotic period, like 18.6 years, over summer and winter, you have changes in the seasonal cycles, which ultimately changes the temperature. So there is a constant change which is also happening, right? So a lot can happen because, and which ultimately leads to the change in the strength of these PSR surfaces, right? So, and then there's another thing that, you know, I thought we should talk about. One is that if you have something like water ice, which it can probably fill up an existing crater, right? And this is not at the PSR, but the effect is that the picture that I have on the left-hand side is at the highland smooth plains. But the effect would be that a part of this would be filled up, and then the crater is going to lose its shape, right? So either because of the change in the strength, the crater itself is different, or you can actually have a crater being filled up. Going a little bit into the degradation of the smaller craters, because that's what we are going to talk about, is that we have this hypothesis that for the smaller craters around this, 300 meters range, when they form initially, there is a fast change because it's forming mostly in regolith. The walls are unstable, so it kind of, there is a fast process which goes to this zone where the depth to diameter of that crater is around that 0.12 to 0.18, after which this really slow, nearly diffusive process starts, leading to the ultimate degradation of the crater. And this ultimate degradation of the crater is a really long process. Like, the initial process is fast. So if I would use something like a morphological freshness classification of like classes A being the freshest and C being the most degraded one, then the C class takes up the maximum amount of time in the crater's evolution life cycle. Right. So, and this is one of our one of our earlier works. What I wanted to show is that for these craters in these size ranges, majority of these craters would be below this line of depth equal to 0.1 times the diameter, and overall, all of them will be below this 0.18 cutoff, and actually even lower. I mean, these ones actually were much smaller craters, so majority of them are concentrated in even lower values. Now, having said all this, we start talking about this thing, and we start thinking about this thing, that the shapes of the smaller craters that are forming at the PSRs, they will be affected if the surface, the target property has been sufficiently altered in comparison to the non-PSR regions. So even during the formation, the craters themselves have a different shape, right? Again, after forming, maybe they get filled by whatever is there. And later on, the degradation processes, they may be different, which again changes their shape in a very different way. So the question that we are trying to kind of get to here is that, can we compare the shapes of smaller craters at the PSRs and non-PSRs? So while we were thinking about it, I mean, we could pick a PSR and then kind of take the craters there and then compare it with another, place. But while we were looking at that, one particular PSR kind of caught our attention, and that's the PSR at the Amundsen crater. And you can clearly see why. The Amundsen crater is one of those PSRs where we have a really flat ground with direct solar illumination right next to a region which is a PSR, right? So, and then this is kind of atypical because it is one of those places where you can actually, it's very accessible in terms of the exploration point of view. It's a whole different discussion though. But the idea is that the directly illuminated zone and the permanently shaded region, they are both on flat regions and adjacent to each other. Now, so before I get into the method part of it, I'd like to show a small simulation. So this is the Amundsen crater. On the left-hand side is the direct solar illumination, which is happening on the walls of the crater. And on this part, you will actually see the indirect reflected illumination inside the PSR. This is a simulation. This whole simulation is over a period of 18.6 years, right? And on the extreme right-hand side, this plot actually shows at what point in the subsolar time, latitude and longitude, where you have the maximum illumination inside the crater, the secondary illumination. But I'll just play that once more. The idea is that at no point, the seasonality idea can be clearly seen here. The green thing here basically kind of indicates that zone where there is no light coming even as direct solar illumination on the walls for the zone that was simulated here. But here you can see that this part kind of changes over the time, but I mean, this is where the PSR, the permanent part resides, but the seasonal thing kind of takes over and goes around in different zones. Now, let's go to the next one. Okay, so what did we do? So for the methods part, what we did is we used the Lola topography because these are PSR, so we do not have images and stereo. So we used the 25-meter Lola topography, and we computed the hill shape, and then we stacked them all together one top of the other. And using max-min operation to enhance the boundaries, we kind of get an image like this, which we then use to actually identify these craters. And this is where our size range of the crater comes from, because the smallest pixel here is 25 meters. So we wanted to take at least like 7 to 8 pixels, and that's where the 200 meters, 300 meters boundary comes in. So if you look at this, this is what we have here. So these craters are all inside the PSR. These ones are outside the PSR. And this one is actually the diviner temperature, which shows that these ones have temperatures, kind of below this 60K mark. And these ones actually have temperatures around 200, right? So what do we see? What we see is that if you notice this line, this is the fresh small craters. And this one is the fresh simple craters from Pike's work. And these ones are the degraded small craters in our earlier Apollo work. The craters here kind of fall between these two. So they are not really very fresh, and they are not completely degraded. So, and then there's another result here, if you look at them, that the depth to diameter ratio of these craters are all below the 0.15 mark. Okay, and then the last result here is about the shape of the crater profiles. So we took 4 craters, A, B, C, and D, and these are marked here. Now, these A and B—
2 minutes.
Okay,
2 minutes.
So the A and B craters are inside the PSR. The C and D are outside the PSRs. They have kind of similar sizes, right? But note that they do not cluster at all depending on where they are located. They cluster depending on their degradation state. So like these two, which is this crater D and crater A, their depth to diameter is like 0.1, so they are less degraded. These ones are more degraded, so this is this is more shallower, right? Which overall, all of this together, what it basically means that there is no distinct change in shape or depth to diameter between the craters inside and outside the PSR. And which leads us to this kind of conclusion that we find that because there is no significant difference, this particular analysis indicates that the surface water ice, if present, it only exists as a very thin layer and is not captured at the scale of our analysis. We are kind of pushing back against of the presence of thick ice. But we do think that if at all, if there is surface water ice, we cannot resolve it at that scale, because otherwise we would have seen some signature at this point. And we would require high resolution images from eminent PSR imaging missions, for example, the KPLO mission, where we'll have the ShadowCam instrument to actually take pictures at these PSRs. which will lead to detailed interpretations of doubly shadowed regions and help us understanding crater degradation states. And, with that, I'll end, and if there are any questions, please.
Okay, thank you very much for the very interesting talk. Excellent work that you're doing there.